Okay, so let's get started. This is Learning Fine-Grained by Manual Manipulation with Low-Cost Hardware by Tony Zhao. The keys in this title to me are the fine-grained manipulation part, and actually in the paper they go on to mention it's not just fine-grained that matters, but also contact revision dynamic. And to just give you a demonstration of what that looks like, here's their project page, actually. And here's some of these tasks that they're referring to when they say fine-grained or dynamic. So here they're inserting a drill bit into a drill. Next one, inserting RAM into a motherboard. So a lot of precision required there. A lot of precision required to insert this blade, and I'll just maximize that. Insert this blade and slice open the tape. And contact rich here because you have multiple points of contact at once, and you need that in order to complete the task. And then the dynamic stuff is stuff like balancing a ping pong ball or bouncing it on a ping pong paddle, which it's dynamic because you can't stop, you can't pause the situation because the world will keep moving without you, so that ball will keep rolling whether you pause or not. So all of these things are, challenging enough on expensive hardware. So where we have like a traditional robotics pipeline where we have a perception component, a planning component, and a controls component, right? Or some variation of this, but there's a lot of hand-coded stuff in this pipeline, and it depends a lot on very accurate hardware. So you need precision and accuracy in your perception, especially if you like relying on point clouds to fit models to objects in the scene. And for your controls, you need to be able to trust that if you say, hey, robot, go here, it goes there to within a couple of millimeters, or depending on the task, really. But you've seen how complicated the tasks are from the videos. And also, if you want to know where the robot is at any time and you want to read out the state of the robot, so the joint angles, you need to have pretty accurate information there. So the question is, how do we unlock low-cost hardware? It's like low-cost enough that if we try to plug it into like a traditional robotics pipeline, it will fall apart. And the inspiration they take is like a lot of machine learning is from humans. So here they say, humans also do not have industrial-grade proprioception, and yet we are able to perform delicate tasks by learning from closed-loop visual feedback and actively compensating for errors. So there's this idea of the closed loop, which you can incorporate that into traditional robotics pipelines. But there's also the idea that we can look at a scene and kind of immediately infer what we have to do, and we don't do it in this modular fashion where we actually calculate things and calculate the pose of objects before picking them up. Our brain does the magic, and we kind of just do it. So in the abstract here, they sum up everything I've just said to you so far. Can learning enable low-cost and imprecise hardware to perform these fine manipulation tasks? Right? So this is what the paper's about, but they go a step further in the abstract and what the paper's about at its core, which is they focus on machine learning and imitation learning in particular, which, as we'll discuss in a moment, has its own challenges. So I'll just read this one. Particularly in high precision domains, errors in the policy can compound over time, and human demonstrations can be non-stationary. So these are the types of challenges they want to address with their modeling approach. Okay, so before I'm going to break this paper up into two sections in terms of the methods, and that's the hardware and the modeling. But before that, I just want to make sure everyone's on the same page regarding the machine learning paradigm here, and the imitation learning paradigm, really. So the idea is that you have like a neural network, a machine learning model, which takes in as inputs observations, right? And these can be like images from cameras. So here in this setup here, which I'll dive into in a moment, we have cameras on the wrists of these robots. We have a camera at the top, and we have a camera at the front. So we have 4 camera views. So cameras, It can be proprioceptive robot state, so the robot reads out the joint angles. And so this is proprioceptive state. And it can be other things, of course, but I'll stick to these two because that's what this paper discusses, right? And, you know, this neural network plugs and chugs all that and gives you an action, right? So in this paper, they'll talk about vanilla behavioral cloning, which is like a specific type of imitation learning, and it's a good baseline to use because it's the first thing that we would reach to, which is you take a snapshot of these observations and you pass it through the neural network and you predict one action, you execute that action, then you rinse and repeat. So then that's how the machine learning model works at test time. At training time, what you want to do is gather lots of data so that you can train this model. So what you would do is you would get a human, or not necessarily human, you would use some means of controlling the robot to complete a certain task. And you may ask, okay, well, you've already got a means of doing it, so what's the point? Well, the thing is, you can use an expensive means or a non-scalable means. So one of those is getting a human to control the robot. And you take a task like picking up a Coke can and throwing it in a trash can, and you make the robot do this task hundreds of times, and you record everything that I've written down here as inputs and outputs. So you record the observation cameras, so the cameras views the proprioceptive state and the actions that the robot is doing to perform the task. And now you have your training data. So that's the framework. That's the paradigm we're working with. So let's talk about the hardware now. What they've done. So they've made this ALOHA, which is a low-cost open source hardware system for manual teleoperation, and they have a couple of design requirements they have for this. One, that it's low cost. Two, that it's versatile, that it can do like a wide variety of tasks that they're interested in. 3, 4, and 5 kind of related to each other, I think. User-friendly. So it's easy to use in the moment, but it's also easily repairable because these systems break a lot and it's easy to build in the first place. So I'll shout out a couple of details here. This might mean more to people who actually work with hardware on a daily basis. But yeah, they use a ViperX robot arm, which is, well, I'll show you the diagram in a moment, which has 6 degrees of freedom. It can carry up to 750 grams, 1.5 meter span. And importantly, it's got an accuracy of 5 to 8 millimeters. So that might not be enough to do. I mean, if you did something like try to take the lid off this cup, here it is. If you did like something like try to take the lid off this cup with 5 to 8 millimeter accuracy in an open loop fashion, you probably wouldn't succeed. Just have a look at the precision here. Okay. And so that arm costs 5.6 grand. And then in order to control the arm, they don't use a joystick or anything like that. They actually use a kind of clone of the arm, but just a smaller version of it. They use, if anyone knows about it, the Widow X arm, right? And that's a bit cheaper, 3.3 grand. And then they set these up as, because it's bimanual, you have two of the bigger arms that actually do the work, and these are called the follower arms, and they're called the follower in the context of the leader arms, which are the ones that the humans control. So that a human will grab this arm in front here by the handle, like you see here, and be able to move it around, and the follower will read out the joint angles from it, and then the follower will use those joint angles as targets. So actually, just bringing the video back, you can see here, just in the background, the person is using the leader arms there. Right. So all up, because there are 2 arms and 2 follow arms, 2 leader arms, they use 4 Logitech webcams, and they have a few other modifications for safety and usability. This comes up to $20K system, which, I mean, someone can pitch in maybe, as I haven't worked with other systems, but apparently this is very, very cheap for what it does. So that's the hardware. Onto the modeling. So, like I mentioned before, there are two shortcomings of behavioral cloning that they're trying to overcome. Like vanilla behavioral cloning, or and that's one is multimodality. So let me explain this to you. And to be clear, this is not, if someone has raised this before, this is not multimodality in the sense of, oh, I have multimodal inputs, like I have some audio inputs, some visual inputs, some natural language inputs. This is multimodality in terms of probability distributions or data distributions. So say I have like a an obstacle here, and at the bottom I have like a robot arm. And this is like top view, or we can work in 2D if you like. And the robot has to get to something over here. Maybe it's a cube that it wants to pick up. And we make the data set in the fashion that I described before, where a human teleoperator operates, a leader arm to make this follower arm move and do the task. Well, okay, so we could have some people who decide to go around the obstacle this way. Some people could go the other way. The same person in one session could go this way, but then get tired and go this way instead and use their other arm, or whatever reason you can think of. But there are two equally valid ways to go here. And you can, I mean, this is just an example, but you can think up situations in which there are more ways to do one thing. And in a vanilla behavioral cloning setting, what we're doing is when we have this, so we have the machine learning model, observations in, actions out, right? So one way to train this, one common way to train this is with regression, with a regression loss. So you have your predicted actions and your data set actions, your true actions. And, you could do mean squared error. So you could subtract the prediction from the true, square that, and take the mean, and that's mean squared error. Or we could use L2 loss, or we could use L1 loss. But all of these, from a theoretical perspective, model a unimodal distribution in your targets. So, and, not talking about theory, just making this a bit simpler. If for a particular data point, the action is to go left, but your model guesses right. I mean, these are both both would be equally valid guesses, but this is going to be a large loss for the model, right? So in order to kind of reduce the loss as much as it can in expectation over your whole data set, the model is going to learn a hedging policy of sorts, right? So it will somehow average these two modes. And here, worst case scenario is it actually smacks into the obstacle after being taught how to do this task. So how do we deal with multimodality? I'm going to mention two methods now, because one is used in the baselines that this paper compares against in the experiments. So the first idea might be, okay, so you say, let's just pick one of the degrees of freedom of this robot. Let's just say the X translation degree of freedom, right? And this is a continuous variable. So we can do, maybe your, this is a continuous variable. So we can do the regression loss that I described before. But the other thing we can do is bin this, like the whole workspace. Say this is a meter span, and we know the robot can't go further left than 50 centimeters to the left, further right than 50 centimeters to the right anyway. So we could bin the whole workspace like this, at least in this dimension. And what this lets us do is, even if we have this bimodal distribution, you may be aware from using categorical cross entropy loss to train a model to predict one of the ImageNet categories, that your model is actually now able to put out a probability distribution over these bins. And then that's a valid output. Yeah, it doesn't have to output like a single value. So it could say, oh, 30% this, 20% this, 30 here, 20 here, right? So you can see now that the model we're able to model multimodality here. So that's a strength. One weakness of this approach is that if you make the bins too large, you don't have much precision. anymore, because if you choose this bin, I mean, maybe this bin's like a centimeter wide, right? And that's not precise enough to do the task we want to do. The problem with making the bins too narrow is it becomes a bit too difficult to learn, because the shortcoming of this type of loss categorical cross entropy is that there is no magnitude associated with how far you are off target. So if you guess here versus if you guess here, the model is equally punished in that, or like the loss is about the same. It doesn't matter how close the bin was to the correct answer. So that's one way. The other way is to use a variational autoencoder. I mean, there are many. So actually, the other way is to use generative modeling, right? And the most famous sort of generative modeling of today is probably diffusion modeling. But there's also variational encoders, which were hot before diffusion models were. I don't want to go too much into explaining the variational autoencoder. So I will assume that you're all kind of familiar with it, and all I'm going to do now is jog your memory. So the idea is that if you want to, if you have a data set of, say, 1 million cats, you can, like, natural pictures of cats, all the cats you can think of in a world. You can make a network, which is called so you can use a variational autoencoder to generate a plausible looking image of a cat. And it's a cat with a smiley face. Maybe I'll put some whiskers on it. There we are. And the way that's made, to be multimodal, or part of the mechanism that makes this model multimodal, is that actually on the input here you introduce what's called a latent variable. Right? It's a compact. It's like, it can be thought of as a compact representation of everything that embodies this particular picture of a cat. And it's abstract, so we can't read into it, but it might have information about the whiskers, about the color of the fur, about the pose of the cat, etc. And actually, this latent variable is sampled. And this is where, like, the multimodality comes from, because we're able to sample on this end, on the input end, from a normal distribution, from a standard normal distribution, right? The way this is trained, though, is you have an encoder, which you don't actually use at test time, right? And you actually give as input to that a picture of a cat, and your training objective asks you to try to reproduce. Well, so you end up encoding into some latent variable, and the training objective is twofold. One, reconstruct the picture of the cat. So if you put in this cat here, the same cat should come out. And two, make sure that, so this is the prior loss, prior matching. Make sure that the encoder produces latents that are within this standard normal distribution. So hopefully that's jogged your memory. Actually, no, there's one more aspect that really matters here. This is a conditional VAE in this paper. So there's one more thing we can do, is we can control the generation of the cat. Like before, I said we could generate any cat, but we don't really have control, because we sample from the standard normal distribution and any cat comes out. But we can tack onto here a label, which we do at test time, matching to the input label, and that will be like a Siamese cat, or a Russian blue cat, or another type of cat, right? And then that means that at test time, we can put this label in with a randomly sampled latent, and we can produce the type, the breed of cat that we're interested in. So that's how they tackle the multimodality. Hold those ideas in your head for a second, because I'll come back to them in a moment when we look at their architecture. The other thing that they wanted to look at is making sure that this is not susceptible to compounding errors. So let me do more drawing here. Say we have like an obstacle, and there's something on the other side that we want to get to. There's a robot arm here. We gather a data set of trajectories that get us to that obstacle. right? And it looks something like this. I'll stick with the unimodal case for now. No ambiguity here, right? And the data set is denser towards the middle, a bit lighter towards the fringes, right? Kind of like a Gaussian distribution. And if all is well and our model is trained well and we start somewhere here with our robot arm, and we predict an action, we might take a step. Actually, let's just say this takes 5 seconds to do. I forgot to mention that the ALOHA setup has a control loop of 50 Hertz. So that's 250 time steps. So if all goes well, we'll query our model 250 times and we'll step along this trajectory. And it'll take us 250 steps to get to the end. But what if we start here, somewhere a little bit towards the fringes of the data set, data distribution? Well, as we know, theoretically, if the data is less dense in a certain place, it's possible that the model won't work quite as well. And it's possible that we might step, further off the data distribution. And now we're in a worse place. And then it's possible again that we might step further off the data distribution. And in fact, if the whole situation here is not two-dimensional but higher dimensional, we're in even a worse spot, because the higher the dimensions, the more likely it is that a step with some degree of randomness in it is going to take us away from the data manifold. So we could end up out here, and the robot arm will start doing crazy things that we don't want it to do. So then one way of mitigating this is to say, actually, you know what? Let's not predict one action at a time. Let's predict 100 actions at a time, right? And what's that going to look like? Well, we go predict, do 100 actions, predict, do another 100 actions, predict, and do another 100. We'll do 50 actions and get to. For compounding errors is drastically reduced there. So that's the idea of that. They have another really interesting aspect, which I like here, which is they didn't mention this in the abstract, but they say chunking can also help. By the way, they call this, doing multiple actions, chunking. So chunking can also help non-Markovian behavior in human demonstrations. Specifically, a single-step policy would struggle with temporally correlated confounders. Actually, I think this is a bit of a word salad right now, so I'll just make it a bit simpler. They're specifically, from another part of the paper, referring to pauses in demonstrations here. So if I were to do a demonstration where I move a bit and then, like, for some reason, all the human operators who are helping collect the data decide to pause here for half a second, and then they continue moving, maybe because they need to think about something because the task is complicated. The problem with this is, with a half-second pause and 50 Hertz control loop, that's 25 time steps. And when we're training our model, the model sees in this region, most often when it's presented with this observation here, it learns that it has to not do anything, don't move. And even if there's a small chance the model decides to make a movement, to put an action out that moves along the trajectory, but then it's still not far away from that spot. So again, it could get stuck again. And so you'd have the situation where the robot kind of freezes and then stutters and then freezes again. But if you have action chunking, right, what you can do then is you can have, this 0.5 second pause will be contained entirely within a 2-second chunk. So a 2-second chunk looks like move, 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 pause, and move, right? So that's another advantage of the action chunking. Okay, so those two design requirements are taken care of. I'm going to maybe spend a few minutes just giving you the details of the architecture so that you can really piece it together in your head, and then we'll go on to the experimental results. Any questions so far? Good. I'm going good for time, so I didn't want anyone to spoil it, to be honest. So I mentioned before there was like a VAE decoder. Don't get confused. They use the word encoder and decoder in two different ways here. And I'm going to point that out to you. But this whole thing here is the VAE decoder, right? And so I mentioned the input to the VAE decoder is the observations and a latent variable. And we hope that the output is the correct action sequence. Well, so the action sequence is our picture of the cat from before. And, you know, our latent Z is here as the input. And also all of this other stuff here is the conditioning, so the cat's breed. But what does the conditioning look like for this robotic setting? Well, okay, so we have our 4 camera views here. And we pass each of those through a okay, so actually, first of all, quick reminder of what a transformer encoder does for anyone who just needs their memory jogged. It takes a sentence, like, for example, in a natural language setting, it takes a sentence like, je m'appelle, I can't really spell in French, but Alexander, right? And turns that into tokens. You need these tokens, right? By using a lookup table or something like that. And then it does a bunch of, well, it does a bunch of stuff, but on the output, you would hope to have tokens again with the correct translation. My name is Alexander, right? So we need a way to, like in this setting, tokenize our observations. So how do we do that? With images, we pass them through convolutional neural networks. So here's a 3-channel image with size 640 by 480, for instance. And that goes through the convolutional neural network to a point where it's like compressed into a feature map of size 15 by 10, for instance, with 512 channels instead of 3. And then you can pick this pixel here from that feature map, and that is one of your tokens. And you can pick the next pixel from the feature map, and that is another token, and so on. So these are all the tokens from camera 1. And you do that with all of the cameras. And the joint state, like the readout from the joints of the robot, is also encoded into a token. So it's 14-dimensional here, 6 degrees of freedom per arm plus grip arm times 2 arms. But then you use like a small neural network to upsample that effectively into 500, like whatever the token size is, 512. So the encoder does all the work of, okay, let's do a bunch of self-attention where all these tokens attend to one another, feed-forward networks, and get up here to an abstract representation of everything that I've put in. And then the transformer decoder does the work of, okay, let's do cross-attention. Let's consider all of these tokens from the transformer encoder and work our way towards figuring out what the output action sequence should be. So that's how that works. Remember, though, we have this latent here, latent variable. And so at training time, we need to actually train the the VAE encoder, right? And if you remember, I was talking about that picture of the cat before, and its analogy to this action sequence. Well, okay, so the VAE encoder takes in an action sequence as well. So that's that same picture of the cat that I was mentioning before. This is a detail, but it also has another token that ends up becoming your Z, your latent variable. And to me, an interesting detail, which maybe we could have for the discussion section later, they decide to put some of the conditioning into the variational autoencoder's encoder. So that's the whole architecture and how it works. There's one more interesting aspect that they talk about in this paper, which is action chunking. So before I move on to the experiment, so action chunking looks like sorry, not action chunking, temporal ensembling. So action chunking looks like this. So we said before, at t equals 0, let's output 100 actions from the model, and let's execute them all. And then at t equals 100, let's output another 100 and execute them all. You can do ensembling by doing this. At t equals 0, output 100 actions. Execute the first one. At t equals 1, output 100 actions, or predict 100 actions. Consider the first one here and the second one from before. Average them somehow, and then execute that, the result of that averaging. At t equals 2, generate another 100 actions. Consider the first one, consider the second one from before, and the third one from before that, and average all of these somehow. And the averaging scheme they use is exponential moving average. They argue that this can help with like noisy model output. But they also, well, I'm not sure if they mentioned this, but a lot of people who have tried this since have mentioned that, temporal ensembling can be quite problematic. And you can imagine that in the case where you have multimodality and no guarantee, no strict guarantee that, this prediction chunk won't choose a different mode from this prediction chunk, you can end up with the problem of, again, smoothing between modes. But actually, we can leave that a bit to the discussion section too. So nearing the end of this, let's look at the experiments or the results. Here we are. So they do experiments on a bunch of different setups in the real world, like the ones that you see here, and also on simulation environments where they can do more rigorous testing. So there's a simulation environment where we have one robot arm picking up a red cube and passing it to the other one, and then there's another simulation where we have a red block with a slot in it and another smaller red block, and you need to insert the red block into the blue block. So both arms have to pick up a block each. And they gather data for these by, they gather 2 data sets each for each of these. One is with human teleoperation, but one is a scripted data set where the robots are, you have access to the internal state of the simulation, and you can script something using classical planning algorithms, and you have importantly a deterministic output. Okay, so what are they? Let's have a look at this table here just to help you get your bearings. We have the cube transfer task, the bimanual insertion task, which is both simulation tasks. And then we have sliding the Ziploc bag and slotting a battery into a remote control. We have a bunch of different benchmarks that we test again, and then ACT. And then each of these are broken up into milestones for completing the task. Like for cube transfer, did you touch the cube? Did you lift the cube? And did you transfer it to the other arm? Let's just focus on the rightmost column for each of these, which is the task completion, for a moment. So they first look at behavioral cloning, which is this kind of simple, one observation in, one action out, and the results are probably the poorest on the whole table, apart from VIN, which is a nearest neighbor like non-parametric method, but I won't talk about that right now. And then then they also test robotics transformer, which has a lot of other features, but for our intents and purposes, what it adds is this discrete binning and categorical cross entropy loss that I mentioned before to kind of model multimodality. It may add a history of observations, but I'm not sure. And so it does better. It does better than the vanilla behavioral cloning. And then there's behavior transformers, which again may add a bunch of other things, but I looked at it briefly, and for our intents and purposes, it does discrete binning, but it does something else, which is once you've selected a discrete bin, it also has a regression loss so that you can fine tune within this bin. So you get the best of both worlds and a history of observations. And that does even better. So, these results so far are encouraging in relation to the thesis of this paper. And then they show ACT, which does the best by far. I think you can look into the numbers yourself and try to interpret that for yourself later. Now on to my favorite part of any paper, personally, which is the ablations. So, we mentioned a lot of features of this action chunking transformer architecture that try to mitigate issues with vanilla behavioral cloning. So let's put those to the test by ablating them away and seeing if they actually made a difference. So one thing that I like that they do here is they implement action chunking in the baseline methods. And they so what they do here is they say, okay, what if you predict one action, or what if you predict 10 or 100 actions, or 200 or 400, right? So if we increase the horizon of this action prediction, the blue line is their results, ACT, and you can also see how much the gap is closed when you also apply action chunking to behavioral colliding, which is the green line, and the nearest neighbor method, which is the gray line. So that's quite interesting. Unfortunately, these experiments aggregate scripted and human simulation data. So I'd like to see the cut, but yeah, that's what we have here. Temporal ensembling was another aspect that I mentioned earlier. They seem to show that it slightly improves. So with temporal ensembling, yeah. So blue is no temporal ensembling, green is with temporal. Slightly improves theirs and behavior colliding, and doesn't improve VIN. There's a comment for why, but I don't remember it. We can maybe discuss that. And finally, the generative aspect is one I personally find the most interesting. So when I mentioned that you can train this, you train with a variational autoencoder or a variational objective, that's actually optional. You can actually just train with a regression loss and get rid of the VAE encoder at training time. And the argument, well, remember the argument for using a VAE is to model multimodality. Now I mentioned that the simulated data had like a scripted version, and they show that because the scripted version is deterministic, using a VAE doesn't change the results. But if you switch to the human data, the human generated data, you get really poor results without using the variational objective, and much better results when you do use the variational objective. So also quite interesting. I'll leave that last one for discussion potentially, because I want to wrap this up. But I think we've just gotten through the whole paper, and I'm keen to hear. Like I know that people here have discussion points about this because you've tried ACT yourself. So I'm keen to hear about those, or if anyone has any questions for me to clarify something I've said before, that's great. But yeah, I'm going to open up to anyone to be able to unmute and say something now. Ashish.
Hey, firstly, great job with the review. Fantastic to have you go through it. I was hoping we could maybe just hammer on the CVAE and how it's picking between the modes. My understanding is that it's conditioned on the image input, but how exactly is it determining, should I go left or right?
Okay, so anyone else is welcome to jump in here if they've got a lot of experience with VAEs. The conditioning is not what makes it choose left or right. The conditioning just says, the conditioning just gives the observation of the current situation. So maybe this is the current situation, and you're at a junction and you have to either go left or right. What makes the model be able to choose either left or right is the fact that, remember, with a VAE, you have like the decoder and you put in a latent variable which you sample from a standard normal distribution. So depending on the exact value that you sample, you may get left or you may get right. And so this provides the kind of non-determinism there in the context of the generation. And at training time, what you're doing effectively, this is my take on it after having spent some time with the VAE literature, is that you're offering this end-to-end model two paths to take, or multiple paths to take, which makes it, I mean, if you don't have this kind of sampling step in the middle here, the output of this model is essentially deterministic if you don't count things like dropout and stuff like that. So then you're always going to get situations where it has to hedge. It has to choose between left and right. But at least if you're providing the mechanism by which the model can get different inputs, then maybe if you sample here, maybe if you sample here, it chooses the left. Maybe if you sample here, it chooses the right. And at training time, you're giving it both options. So then when it jointly optimizes reconstruction loss and prior matching loss, it's able, like in expectation, it's able to, well, I kind of lost where I was there, but I think I was saying it's able to choose both paths. Remy, you've got your hand raised.
Yeah, just intuitively during training, you actually encode. I mean, the input of the BAE encoder is the camera images, the state of the robot, and also the target trajectory, the target action that you need to predict. So that's what you encode in your latent space, which is actually a few dimensions. So you encode the style of the trajectory that you need to predict. And so this style can be go left or go right. And at evaluation time, you don't have access to the target trajectory. So you sample it. And that's how you decide to go left or right. I don't know if it's a bit more clear.
I think that really helps, reminding that actually also the input is either left or right at training time. And in order for the model to balance all of these losses, the reconstruction loss and the prior loss, it's going to have to take lefts and put them somewhere and rights and put them elsewhere in the distribution, essentially. And it can't put them in the same place, because if it tries to put left and right in the exact same place in the distribution, what's going to happen is the decoder is again going to have the same trouble as a standard regression loss, because it's going to get the same inputs, right? So, well, yeah.
But great. And just so I can confirm my understanding, so at the start of the trajectory, it's multimodal. I have a lot of options, but I'm going to get a trajectory 100 steps down one path. By the time I've done those 100 steps and I'm calling for the next pieces of the trajectory, my multimodal distribution might only have one mode, which is to continue down the left. Is that correct?
Yeah, I mean, like if I bring up the diagram that I drew earlier, well, I had these like paths to the left and paths to the right, and then like say you do 100 steps starting from here where there's a like kind of multimodal decision pathway. You end up here, now you're in a unimodal decision pathway, and so if the model's behaving correctly, it should just go. It will never flip to the other side, because the data set doesn't say anything about, hey, jump over the obstacle. Michael Fatemi, you raised your hand, and guys, feel free to just talk. If it gets out of hand, we'll go back to hand raising. Makes it a bit less formal.
Okay. Yeah, I was wondering about sort of how variational autoencoders relate to diffusion policy, especially because I guess like you can guide the sampling from a diffusion policy maybe towards a particular mode if you wanted to, which might make it like more interpretable than a variational autoencoder. Or are there just like different like methods of achieving the same thing, I guess?
Yeah, I'm not brave enough to try to sum up very concisely what the differences between what the theoretical, consequences of the differences between diffusion models and VAEs are. But yeah, you mentioned something about being able to like steer the diffusion model towards a certain mode. I mean, you can do that for instance with in-painting. Like if you wanted to head down a certain path, you can like give it the beginning of that path, for instance, and then it has to fill in the rest of the sequence. And there are other steering methods as well. But I mean, I think you can apply conditioning in variational autoencoders as well. I don't know if someone else has comments here.
Yeah, maybe also intuitively when you compare ACT, so conditional VAE, and diffusion policy, at inference time, you can also see a sampling. So in the VAE, you sample at the entrance of the decoder, at the input of the decoder. And for the policy, yeah, you sample noisy trajectory that you decode. And so same that about this example, you could sample something and you would go left. You would take a left trajectory, or you can sample in another place and go right. there is this similarity, but just diffusion is more powerful, even for image generation.
Um,
That makes sense.
I was going to
Thanks.
ask a different question, so go ahead. Okay, sorry. Have there been any experiments using ACT without the overhead camera and just relying on wrist cameras?
I feel like that's one for Remy or someone else.
Yeah, actually, we just did one experiment like that where we were just training on one camera instead of the four for ALOHA V2, and we are just training a very simple policy to node to grasp a Lego block and node, and somehow using four cameras was much better. And yeah, I think having another point of view allows to understand the depths and have more context about the situation.
Right. Because I think high level, and I don't have a great grasp of it, there seems to be, two paths you can go with, cheap robot manipulation. It's either the ACT path, which I think the benefit is that you can get better precision, where it does require, more cameras, a bit more information, and it seems a little constrained. Versus diffusion, where we've seen really promising things with the UMI gripper. So I think they're also working with Cartesian end effector poses, and they only have a on wrist camera. Any sort of general thoughts on choosing between the two and how people compare those two paths?
I think, we can also compare, the Tesla Optimus robots. It doesn't have wrist cameras. So the cameras are in the head. And somehow it can achieve quite good precision. But so there is this path also. The advantage of having the wrist camera is that you don't need a really expensive camera, and you can see very close. So it's much better when you don't have touch sensors, like very good touch sensors. So yeah, I don't know if it addressed your question, but basically you can do a lot with. All the question is to reach the limit of your sensors before trying to assemble a more expensive suite of sensors, I think.
Yeah, I think the other part of that question also was like diffusion policy versus ACT. Was that right, Ashish?
Yeah, that's correct. Just pros and cons between the two, because they seem to solve similar problems, but I'm guessing they have strengths and weaknesses. I just haven't played with them enough on hardware to really get a sense.
Yeah, maybe a few words on this. So I think ACT is really nice because it's quite easy to understand, I would say. Even if you remove the VAE part, it can work pretty well. So it's useful to iterate and to debug. And I think if you have enough context, so for instance, you have a few frames, a few past frames, you give it to the policy, so you have a kind of memory. You might have enough context, sorry, so that you avoid this multimodality. So of course, for the first step, you need to choose, but once you pick a trajectory, either left or right, you have the past context and you keep following the trajectory. So sometimes having more context is much easier than having a really strong model able to model this multimodality. So I would say same. I would like to push ACT even without VAE up to the limits, and then move on to more powerful modeling with diffusion.
I mean, I'm curious to know, more about. I mean, so Remy, in your experience, do you think like VAE is actually detrimental, like using the variational objective? Like I'm quite convinced by what they've presented in the paper, especially like this table, this graph here, where it's just like scripted data, the VAE has no positive impact, and the and for the human data, the VAE has a huge impact. So like, what is your stance on that? It's detrimental, or just simply not helpful?
No, I think I mean the results are really interesting. It's just that sometimes you need to tune the VAE really well. So it's a bit complicated to make it work. And it really depends on the data set that you have. There are some data sets you actually don't really need to model the multimodality. So yeah, I think I prefer the diffusion policy approach. Because yeah, it's more general, easier to tune.
Yeah,
But yeah, so
yeah, that's right. And the other thing I find interesting is the temporal ensembling. They seem to mention it in the paper. They go to the the effort of showing the ablation table, but it just doesn't seem they went all in with that. Because, well, I think that in the final models that for example, in the configuration on the original ACT repo, they have that disabled by default. They've chosen blue here to represent like their main model. And so in this table here, it's no temporal ensembling is the blue one. And then, people, I don't know, on Twitter or other places have just mentioned that it kind of doesn't work for them when they turn it on. We've implemented it in LeRobot. We added it recently. So who's tried it and found that it works or doesn't?
I haven't tried it, but it could just be considered as like a heuristic-based regularization, right? So it's not like theoretically liable to work, but it's just a reasonable approach.
Yeah.
yeah, it's an interesting trick to smooth the predicted trajectory, to average them over multiple timestamps and predictions. But ideally, you would like to have a really fast reaction time. And so it would be nice if we could avoid using it so that, yeah, as soon as you have something that show up on the camera, or I don't know, the Lego block is falling and you miss the graphs a bit, you can react very quickly. So yeah, that's the benefit of not having this post-processing, the ensembling. But then maybe your trajectory can be less smooth if you don't have enough data.
Yeah, I mean, it's not just the post-processing; it's also the fact that you're doing model inference every single step rather than every 100 steps. Sorry, whoever that was, please continue.
Yeah, so quick question, Alexander. So first of all, thank you for the presentation. And on the histogram that we see currently, could you maybe you've talked about this a bit, but why is it that performance, I mean, the success rate is much better when using scripted data rather than human data? I assume that it's like human data must be much more noisy, and so maybe a bit more difficult to learn.
Yeah, so this is that diagram I was showing before. Remember when I was saying, okay, so the robot arm's got two ways to go around the block and they're equally valid. So it could go this way or it could go that way. And I described why a human data set would cause this sort of data distribution, because people are different, and even within one sitting, people can decide to do different things. This scripted approach was designed to be deterministic. So, and I'm not sure okay, so I'll get into that in a moment, but it was designed to be deterministic. So when presented with this situation, no matter what, it would always choose the right path, right? And then so you'd always have a unimodal data distribution. I mean, there's the question of like, well, if how deterministic is it, and how sensitive is it to initial conditions? If I nudge the robot arm to the right a tiny bit, or to the left, will it always choose the right path? I'm not sure, but their point is that it is deterministic to the degree that they care about. So it's unimodal versus multimodal. Does that answer your question, Simon? Or not?
Yeah, thank you.